Hey there, and welcome to my first video on applications of differential equations. So the purpose of this video particularly is to illustrate how we can use separable differential equations to create position, velocity, or acceleration functions uh, based off of what we've already seen of them in calculus. Because we understand that early on, in differential calculus, you understood that uh, the position function, if I take the derivative of that, produces the velocity function, and if I take the derivative of velocity, we wind up with acceleration. And now that we have studied some integral calculus, we understand that the indefinite integral of something is the antiderivative. So if I have acceleration, I can therefore find the velocity and therefore position function. And they're going to be presented to us in a separable differential equation uh, method or way of presentation. And we're going to be using our skills for either integrating something or taking the derivative of something to uh, create a position, velocity, or acceleration function. Now, that's not the only application of differential equations here, but this is how we're going to be looking at it because we are going to a lot of times be looking at something as far as how do you figure out how fast something is moving at a given point in time. Is it accelerating or is it decelerating based off of the signs? And where is it at a particular point in time? Now, coming down here to the paragraph, you can see that we're going to be looking at a lot of things in terms of a body in motion. And physics students, this should be very familiar to you, ignoring air resistance. We're going to be looking at how things accelerate due to gravity in a free fall motion. And that's again, something that should be familiar to you from either previous studies in your calculus class or in physics. The gravitational constants that you should be familiar with are in feet, negative 32 feet per second squared, or meters, negative 9.8. Now, negative 9.8 is not exact. It's, we round that number, but it's close enough for what we need to do. And this is essentially your acceleration function, negative 32, or we have an acceleration function of negative 9.8. And that is essentially what the acceleration functions are. Now, moving on here, we see that they're writing the acceleration function as a differential equation. So we've already seen up top that acceleration is essentially just whatever the value of the gravitational constant is. But we can write it in the form of a differential equation and therefore be able to separate it and solve it so that way we can identify what velocity or acceleration would be. And that's exactly what we're going to be taking a look at first. We're taking the separable differential equation that we have here and we want to solve it to get a general velocity function. This is not going to be a specific velocity function. It's just going to be a general function because we don't have any initial conditions. So separating it, we're going to wind up with dv is equal to negative g times dt. Now, in previous separable differential function lessons, at this point, once the variables have been separated, where in this case v is on one side and t is on the other side, what you would have done is we integrate both sides. So on the left side, when we take the derivative dv, that's just going to give us a v. And if you want to, on the other side, if it makes a little bit more sense, you can take the constant out and just say that we're taking the antiderivative of dt, or you can leave it there because these two things on the right, they essentially are the same thing. It's just that in one, in the way it's written on top, the constant is left inside of the integral, and on the one on the bottom, the constant has been pulled outside of the integral. But either way, we take the derivative of both sides, and here I'm going to change it to be v of t, since we are creating a function with respect to time, and that will be negative g times t, and we have a constant. Now this particular constant, because we're creating a velocity function, c, and let me go ahead and do this in another color here. So c in this case is the initial velocity, which in equations is usually represented as v naught. So now we have our velocity function. And the next step would be to, now that we have the velocity function, can we have this separable differential equation that we see here? Can we now take that and solve it so that way we can create the position function? And obviously we can. We will take the same process, separate the variables. So on the left side we'll have ds, and on the right side we'll have the negative g times t plus the constant that we found, and all of that is going to be multiplied by dt. And now that we've separated the differential equation, we take the indefinite integral of both sides, take the antiderivative. So on the left side, we're going to wind up with s when I take its antiderivative, and on the right side, when I take the antiderivative of, and again, if you want to, you could pull the negative g out as a constant, otherwise just leave it there. The antiderivative of t will be 1/2, and the negative, and that's not a very nice looking 2, let me fix that 2. So the negative on the g makes the 1/2 negative, so we have negative 1/2 g times t squared. Now the antiderivative of the constant c is just going to be whatever c is times t, but because we're taking an indefinite integral again, we have another constant that I'll indicate as c sub 2 to show that they are different. And in this case, and let me go to a different color here. Usually what we think of as C2, that is the initial position of whatever particle or object that you're talking about is, and that is usually thought of as S naught, like that. Not snot, but S naught. And that is where we're coming up to. So this is the final kind of equation there, but it really should resemble functions that you've seen before, where we say S of t is equal to negative 1/2 g t squared plus v naught times t plus s naught. And depending on the gravitational constant, you could see it as s of t is equal to, if we're talking about feet per second squared, for, you know, if we're just talking about things in terms of feet, the negative 1/2 and g, or negative 1/2 times 32 would give me negative 16 t squared plus v naught times t plus s naught. Or if you were doing it in terms of meters, you would get s of t, so half of 9.8 would be negative 4.9 t squared plus v naught times t plus s naught. So these are equations that you've probably seen and used in the past, and hopefully now where you're seeing how you do the differential equations or the derivatives, you see where they come from, how they came into existence. So we're going to pause here. The second video that I'll have for this will be how we actually use this skill of creating the position function or the velocity function using antiderivatives to write their functions and then evaluate them to determine how fast something is going or where it is in a certain instant of time. But until then, thanks for watching. Take care and be safe.